Okay, I'd love that. All right, welcome back, everybody. Math 131, Lecture 13, the day before test number 2. Test number 2 is going to consist of Chapter 1, Section 8, which is the derivative as a rate of change. 2.1 to 2.7, this is using your derivatives for curve sketching. First derivative tells you to go up or down. Second derivative tells you where it's concave up and where it's concave down. Possible inflection points. Okay, Chapter 3, Section 1 is the product and quotient rule for derivatives. 3.2, which I waited till last lecture, was the chain rule because I wanted you to see a reason other than what you'd already done with the general power rule for doing the chain rule. And 4.1 was your review of natural exponential functions, and we learned to take the derivative of y equals e to the x as well as y equals e to some function of x. And right after class I had a question. Anyway, we're going to start at 4.3 and sort of work backwards and get some questions. Then I hope we get back on schedule. I'm a little bit behind what's supposed to be. Jumping in Chapter 4 for Test 3 material, which is our natural logarithmic function, which is a review from your pre-calculus. We're trying to get to the derivative of the natural logarithmic function. Okay, at the end of class on Friday after the tape, somebody asked me this question, or similar to this. So I want to ask you here as an audience, what's wrong with this? All right, the problem was y equals e to the 3x, and the derivative, so I got a question mark here. Is this the derivative? It's not the derivative. What kind of rule does this look like as we're trying to do or something if we brought the... Looks like we're trying to do the general power rule. And the general power rule was for algebraic functions where you had y was some function of x raised to a constant power. This is not raised to a constant power, it's raised to a variable power. So you have a constant raised to a variable. General power rule is a variable or a function of x raised to a constant power. Okay? So we learned, or I told you and you believed me and trusted me, that we have a chain rule for e raised to some function of x. And your book had several different ways to look at it. This is page 255 in your book, page 255. And I chose to go with the u deal because we're going to go into integration, and integration using substitution, we use u's. So it's going to be the reverse process of taking the derivative. But you had two rules on page 255 when you have a exponential function, and this is a natural exponential function. E raised to some function of x is e raised to that function times the derivative of that function. But I went with the chain rule 1a, where u is a function of x. So e raised to the u, where u is a function of x. The derivative is e to the u. So it's e to that function, just like you see it, times the derivative of the u part. Okay? All right, so if we're back here with y equals e to the 3x, this is a constant raised to a variable. So we're not going to look at the general power rule there. We're going to look at the chain rule. So we'll be using the chain rule. And if you use my u's, it's basically e raised to the u, where u is a function of x. So what's the derivative? E to the 3x? E to the 3x, that's e to the u, times the derivative of the u, which is 3. And you normally write it as 3e to the 3x. And when you put this in WebAssign or any mathematical software, you don't put the letter e. What do you use? EXP. So for this problem, some of you are telling me WebAssign will let you do 3EXP. I'm always covering myself. I would put 3 times but you're saying it lets you get away with not doing that. EXP, and in parentheses, I would do 3 times x again. So 3 times e to the 3x. And with upgrades in software, you may get away with not having the times in there. Okay, everybody good? All right, so I want to start at 4.3 and work backwards because we haven't really cleaned it up. And I'm going to go directly to the exercises in 4.3. And let's see if we see a problem here. In fact, I want to start in the first part of the exercises on 258. And let's just look at the first 2 columns, 1 through 14. And I want you to, let's pick one to do. I think we did number 14 in class on last time. Is there a problem in 1 through 14 you'd like to do as a class? Pick it.
3.
Number 3, that's way at the beginning.
13.
Let's do 3 together. What's the derivative of 1? 0. What's the derivative of 4x?
4.
All right, and this is a e to the u. So the derivative e to the u is? All right, so it's e to the minus 2x times negative 2. Who asked me for this one? What did you miss? Just tell us what you missed. It's okay.
No, it just looked long. I just thought.
Oh.
It looks fine.
Yeah, well, at a glance, in the beginning, it did look long, so yeah. Yes?
What work would you show on the test if you said use the chain rule?
I wouldn't say use the chain rule. I'd say find the derivatives.
Oh, okay.
And for this, there's really not a whole lot of work to show. You would go 4 plus e to the minus 2x times negative 2, or you might go 4 minus 2 e to the minus 2x. There's not a lot of work you can show there. You're right. Thanks for asking. All right, so which one? Let's go where it looks really bad. Which one? 12 looks really bad? Okay, 13 is not bad. Who asked for 13?
I did. It was just a long stuff in it.
Y'all are scared when it's long. This is just a e to the u, correct? So let me put on my glasses so I can see all those little numbers. All right, so this is just e raised to a power. So e raised to the x squared minus 5x plus 4. Let's do this in unison, everybody. The derivative is e
Raised to x squared minus 5x plus 4
times,
2x minus 5.
yes, so it's just e to the u, just like you see it, times the derivative of the u part. So don't let anything long scare you. You know the rule. All right, and what other one did you say looked bad? Y'all are scared to tell me it looks bad now.
I know.
Okay, what would you do in number 10?
I can't see it.
Oops, there you go. Number 10, how would you work that one? Start out with the general power rule because something's raised to the third, so you bring the 3 down, rewrite exactly, decrease by 1, and then what is the derivative of e to the minus 2x?
Minus 2 e to the minus
Okay, minus 2 e to the minus 2x, and then what's the derivative of minus 2x? Minus 2. Okay, so you just start out with the general power rule because you don't care what's inside the parentheses. Then times, oh, I think we did that one in class because then we had to go back and put little parentheses times the derivative of the inside. All right, so which one did you say looked bad? I forgot.
5 and 12.
5. Let's hear how you read this one. 1 plus t times e to the t squared. What rule are you using? Product rule. Let's do it together. We'll do it on blue. Okay, number 5. F of t equals 1 plus t e to the t squared. All right, so when you hear yourself say the problem, if you hear times in there, you know you're going with the product rule. Product rule, what's that, everybody? First, just like you see it. All right, when we get ready to take the derivative of the second, we notice that's e to the t squared. E to the u. The derivative of e to the u is e to the u, just like you see it. This little part right here is this whole little thing right here is my u. So the derivative of e to the u is e to the u times the derivative of the u part, which is 2t. All right, so we got the first times the derivative of the second, plus second function, just like you see it, times the derivative of the first, which ends up just being a 1. Derivative of 1 is 0, and the derivative of t is 1. Okay? They look worse than what they are, don't they? What was the other one that you thought looked a little bad?
We can just leave it.
Yeah, number 12, the reason it looked bad was because you had that 10 in the denominator, and you're correct. We did do that one. But if you rewrite it as just 1/10 times that, it looks easier. All right, let's go to the next columns, 17 through 26. Which one looks really bad? 20? You think 20 looks nasty? Okay, let's try 20. Okay, so you have f of x equals, okay, I'm going to raise it to the 1/2 power because it's a square root. And we got e, oh, help me to make this look easy. How do you write a e to the x over 2 to look easy? 1/2 x. Doesn't that make it look a little easier if you write it as 1/2 x? Yeah. So e to the 1/2 x is the same thing as x over 2 plus 1. All right, so the whole thing's raised to the 1/2 because it's a square root. And then we have a e to the x over 2, which is the same thing as a 1/2 x. If you'll do that little multiplication deal instead of the division when you got a constant in the denominator, it just looks so much easier. All right, take a half a second and find the derivative for me. All right, everybody bring the big 1/2 down, rewrite exactly, decrease by 1. Everybody good so far? Yes, we're going to have good grades tomorrow. Now we'll take the derivative of the inside. And this is a e raised to a u. So the derivative of e raised to the u is e to the 1/2 x times the derivative of the u part, which is a 1/2, and then the derivative, of course, of this plus 1 is a 0, and there we have it. Not too bad, is it?
And we don't have to simplify.
Well, it depends on what your instructions say, and I can't remember exactly on this test, but usually, when I'm really trying to make sure you know rules and the problems are kind of complicated, I don't ask you to simplify. If you simplify, it's usually something that's pretty straightforward. Okay, I'm scared to say this on tape because I don't know what I was thinking at that moment, but if you had to simplify this, really it's not too bad. This negative 1/2 power, this is all multiplication. So, you can just kind of draw your little division line through here. And so bring the negative down in the denominator. So here's your 2. Bring your square root down. And that's a e to the 1/2 x in the numerator, and there's another 2 down here. So it's really e to the 1/2 x over 4 square roots of e to the 1/2 x plus 1. So it's really, oops, I'm about to put a plus c like I was integrating. All right, so that's really not too bad to simplify. It just looks bad, but it's not. All right, number 26, nobody asked for that, but we haven't reviewed that rule. So we'll review the rule with problem number 26. Problem number 26. We've got to find the derivative. And I'd like to hear you say this so you'll know what rule to use. What is it? 4x squared divided by x squared plus e to the 2x. When you hear divide, you think quotient rule. Go for it. Okay, and why don't I put somebody's paper up so that we'll see if there's any mistakes. Okay, have you got it? Great. Did you use proper notation? Good for you. All right, let's look at this and see if we believe it's correct. All right. Let me make sure you copied it down right. Yes, perfect. 4x squared over x squared plus e to the 2x. So we're going to use the quotient rule. You're either going to yodel or bottoms and tops. So here's the bottom, which is the low. Derivative of the top, 8x, minus the top, times the derivative of the bottom, which is the derivative of x squared is 2x. The derivative of e to the 2x is e to the 2x times 2. And there's a nice little set of parentheses here to mark that off. You did it. I just kind of highlighted it for you. Over the denominator squared. I'm going to give her a big old check. Good old check there. Very nice. Very nice. All right, everybody good? All righty. I think we're good at 4.3. Derivatives of e to the u.
Is there going to be a lot of these on the test?
Well, there's not a lot of anything on the test, right? You get one or two to make sure you know how to do it. All right, everybody good? Your tests are not padded. It's a sampling of everything to make sure you're good. All right, so we're good at the derivatives of e to the u. All right, now this is going to look like a piece of cake after e to the u. Let's go back to page 253. Page 253. And the main part I'm real interested in at the moment is that you can do derivatives. I know you know how to solve exponential equations. This other part right in here is just review of pre-calculus, solving equations where you solve for x. By the way, just looking at number 22, what would x have to be? So if you had e to the minus x equals 1, what would x have to be? E to the what would equal 0. So it would equal 0. 20, e to the 1 minus x is equal to e squared. When the bases are the same, what do you do to the exponents? Set them equal to each other, right? Bases are the same in an equation. If e to the 1 minus x is equal to e squared, then those two exponents would have to be equal in an equation, correct? Okay. All right, let's look at some derivatives here. Let's look at problems 25 through 36. 25 through 36. What rule are you going to use in number 31? Product rule. Did you hear yourself say x times e to the x? So you know you're going to use a product rule. What rule are you going to use in number 28? You can use a quotient rule. What else could you do?
Negative to the negative 1.
Okay, since there is not any variables in the numerator, you could write this. I'll just write or. You could rewrite this as 1 plus e to the x raised to the negative 1 and go with your general power rule. So quotient rule works fine because you'd have the bottom times the derivative of the top. Derivative of 1 is 0. So you can use quotient rule or you can bring it to the numerator and use your general power rule. Everybody good? Okay. How do you deal with number 37 when it says find the point on the graph where the tangent line is horizontal? What are you going to do? You're going to find the derivative and equal to 0 because wherever your first derivative is 0, you have to have a horizontal tangent line there. Now that may or may not be an extreme point, okay? But this only asks you to find where you have horizontal tangent lines. Everybody good? Next page. Let's look at the top up here, 254. I almost think we did this. Number 41, what would you do here? Find the equation of the tangent line to this curve at this point. Equation of tangent line. What do you need? You need a slope. How do you find a slope? Take the derivative, and then you go back and substitute in a 0 where you see an x. All right, so that gives you the slope. And once you know the slope and a point, you can write the equation for the tangent line. All right, did 4.2 look pretty easy? Answer is yes. All right, let's go back to 4.1. That shouldn't take but a second. That's just a review of exponents using your rules. I think we did a couple of these in class. This is just where you're trying to get, I know we did number 2. This is where you're trying to, in number 4, you're trying to get a base 3 or a base 2 raised to a power. So for number 4, would you think that needs to be a base 2 or a base 3 when you rewrite it? 3, right? Let's just do that one. So 9 to the what's the easy way to rewrite minus x over 2? Minus 1/2 x. It just doesn't look quite as scary that way, does it? So 9 to the minus 1/2 x. If you were going to write this to a base 3, I gotta change this to a base 3. I need it 3 to the second power. 3 squared is 9. So the only thing I've changed is the 9 to the 3 squared. And then properties of exponents. You got a power raised to a power. What do you do with those? Multiply. So you'll have 3 to the minus x. So the question is, what is k? And the form is 3 to the kx. So in this question, k is -1. Okay? K is -1. All right. I don't think they were too bad. Do you? All right, let's go back to 3.2, which we did very quickly last lecture when I was trying to get you into the chain rule. Chain rule. And my chain rule that I like to use was on page 226, right in the middle. When you had y in terms of u and u in terms of x, and again, the reason I do this to you is because when we get into integration, we use u's for substitution. That's just tradition. So I try to teach it that way. So when you have y as a function of u and u as a function of x, then dy dx is dy du du dx. And you can sort of see that the du's almost kind of cancel out. All right, the example is down in 5. Y is a function of u where u is a function of x. What they were trying to do was say, pretend that you had this problem. X squared plus 1 raised to the 5th minus 2 times x squared plus 1 cubed plus 8. So if you were going to take the derivative of this function, you would have normally just used the general power rule. Well, when you look down at the bottom of the page, it's going to look in the end like you used the general power rule. You brought the 5 down, you rewrote, you decreased by 1. There's the derivative of the inside. They've already factored it out of the whole thing. And then you would have brought the 3 down with the -2, rewrote, decreased by 1 derivative of the inside, which was a 2x. So they've factored out the 2x on the outside for you. But they were just saying, call what's inside the parentheses here the u. So the derivative of y with respect to u is 5u to the 4th minus 6u squared. And then the derivative of the u part is 2x. So dy dx is dy du times du dx, and then go back and put in what the u's are, and there you have it. So the general power rule at that point looked like it took care of all your needs. But when you got to e to the u's, or we're going to get to natural logs of u's, where u's are a function of x, then you see you really need a general power rule. I mean a chain rule. All right, everybody good? Okay, so in 3.2, let's see if we just see an example here. It's been a long time since I've ever given a problem like number 37, where I say y equals u to this, where u is this, because I want you to be able to apply the chain rule for e to the u's and natural log of u's. And if you were doing trig functions, you'd have to use the chain rule with u's. But you don't get to trig in this class. All right, so if I were just looking at number 37, I just want you to realize this is the same problem as y equals 4x plus 1, just making that substitution for the u raised to the 3/2. So if you did the general power rule, it's going to work just fine for you. Okay? Not much in 3.2, although a very important concept for natural exponential functions. All right? 3.1. Let's look for a hard one in 3.1. This is page 221. 221. You're taking derivatives in this first column. You see anything looks bad?
17.
17 looks bad? It does look bad in the beginning, but I bet in a second it's not going to look too bad. Let's look at number 17. 1 over pi. As soon as you see 1 over pi, what does your brain say? It's just a constant. The derivative of a constant is 0. All right, the second part, so the derivative of 1 over pi is just going to be 0. And then you got a plus here. All right, now for the second part here, it's a number 2. 2 divided by x squared plus 1. What rule would you use? You could use the quotient rule, or what else could you do? All right, you could rewrite this as 2 times parentheses x squared plus 1 to the negative 1. So quotient rule is absolutely perfect, or you can rewrite it to a negative 1 power. Is that good enough? Let's find another one that looks hard. Anybody see anything that looks hard? Well, good. I'm 26. All right. Let me write down number 26. Okay, so this is page 221. Looks like I have a mess up here. Page 221, number 26. We have y equals x plus 2 over x plus 3 times x plus 4. And you got to find the derivative. Let's just brainstorm on some things you might do. What might you do? You might do the quotient rule. That's a good start. Looks like then you're going to have a product rule in the denominator. Now, remember, when you get ready to take the derivative of a function, you can actually simplify it before you take the derivative. And so you may prefer to make your life easier because that denominator multiplies out so nicely. Rewrite that as x squared plus 7x plus 12. And then when you take the derivative, your final answer is not going to be so messy. All right, so you could either use the quotient rule, which some of you hadn't learned yet, so what is it? I'm going to go with the first one just because that's the way you asked me, but you could do simplifying the bottom. All right, what is the quotient rule? The low. Y'all like to yodel. Times the yo d high, so the derivative top is 1, minus, be sure to use parentheses, high, to low. All right, so if you left it in this form, what are you going to have to do? Product rule down here, right, for the derivative of the denominator. So you'll have the first times the derivative of the second, which is 1, plus the second function times the derivative of the first, which is 1. All right, make sure the rule works. Low d high minus high d low over the low squared. All right, and that looks pretty bad, but if you had multiplied it out first, it's going to look a lot nicer, and it's the very same derivative. Okay? Questions on that? All right. Are we good, everybody, in section 3.1? Let's see. Let's keep looking on page 221. Equations of tangent lines. You just got, in 29, you just got to do a product rule to get the slope. And then put your 3 in to get the slope at 3. And then go with your equation for a tangent line. Let's see what's on the next page. Oh, we did 33 in class one day, I think. I think you asked me, didn't you? 33. What question is 37 asking for? Can you see it? Second derivative. So you're going to do a first derivative and then do a second derivative. Okay. Let's just set up one of these. These are actually optimization problems. Right here, let's set up one. You want to do, look over 45 and 46, and I'm going to let you pick the one we want to set up. 45 or 46. All right, which one's the class voting on, 45 or 46? 46. Oh, you couldn't even see it. I'm sorry. 46. I know why you picked 46. It's got more words. I know this class. It's too long. Your attention span runs out on the second line. All right. Okay, we're going to set up number 46. Everybody okay? All right. Start with, what are we working with? Closed rectangular box. If it's closed, that means it has a top to it. Rectangular box to be constructed with one side being 1 meter long. Okay, we can deal with that. So let's draw our little box. I'll bring the question back in a second, but I need to draw as I read so that I can visualize what's going on. All right, so this is page 222. We have a rectangular box. I know your boxes look better than mine. Okay, and I'm going to sort of highlight the bottom because sometimes you can't tell on my box what's what. You see the bottom of my box? Hey, on screen it looks pretty good, doesn't it? The answer is that yes. All right, it's to be constructed with one side to be 1 meter long. So I'm just going to pick one side to be 1 meter long. Okay, so I guess we'll call the front a, do y'all have a preference for letters? It's anything you want to call it? X. Maybe you want to call this H for height. Okay, so the bottom of my box is a 1 by X, and then we got a height H. Okay, a closed rectangular box. And let's go to the last part of the question so we'll know what we're going to be maximizing. Find the dimensions of the box with the largest volume. So what am I going to be maximizing? Volume. And then we just want to make sure on this particular box we only spend $240 in materials. So first we're focusing on what we need to maximize, and then we'll worry about it. Okay? All right, so everybody agrees, maximize volume. All right, so we're going to have to get the volume formula. And usually what I do is I do a little max under there so I don't get lost knowing that this is what I got to take the derivative of. All right, so for my box, what is the formula for the volume? Okay, you get the area of the bottom, which is x times 1, multiply it times the h. So nicely, it comes out to be xh, right? All right, and what's the problem with taking the derivative now? That's every box in the whole world that has 1 meter on one side, any x value, any h value. All right, so that's every box in the world that looks like that. All right, but we're only interested in a box that we're going to spend a certain amount of materials on. All right, now let's go back to the words. Have you got your, can you read along, or have you got your book? So we're on page 222, and I'm just going to keep writing things on the picture here. All right, the last line says we cannot spend but $240. on our box. We have a restriction here of 240. I guess I should use a pen here. All right, so the cost of our box can only be $240. All right, the materials for the top cost $20 per 1 square meter. So the top cost $20 per 1 square meter. Per 1 square meter. All right, $20 per 1 square meter. All right, how many square meters are in the top of my box? X times 1, right? Because you have to get the area. It's per 1 square unit of area. And in mine, it has X times 1, or X square meters, and it's $20 for 1. Remember when we first did a problem like this, I pretended this was like a 3 by 3. So the area of the top would be 9 square meters. So if it's $20 for 1, then for the whole thing, it would have been 20 times 9. All right, so for the top, we will have $20 times, I'll just say X times 1. That's the top. Okay, the top is a X by 1. Okay, the material for the sides and bottoms now costs $10 per square meter. So everything else is going to be 10. Okay, so this is top. Cost for the top. And now let's get the cost for the bottom. We're just going to add all these things together. All right, the bottom costs $10 per square meter, so I have X times 1, so we got 10 times X times 1 for the bottom. All right, let's get the sides. Got to be careful, it's not a square base box. Let's look at the side. What's the area of this side? 1 times H, right? And so the other side is 1 times H. So we'll have 10 times 2 times H times 1. All right, so H times 1 is a side. We have 2 sides, and it's $10. Does that make sense? All right, now let's do, it's not a square base box. Let's look at the front, the 2 sides over here. Okay, now let's go to the front and back face. Let's go to the faces, which I call front and back. What's the area of this front face? XH, and the back is a XH. So it's going to be 10 times, and we have 2 XHs. What you were remembering, and somebody else asked me about this already, if you have a square base box, it would be an X by X. Then all sides and faces would be the same area. Okay? That was your question at the beginning. Everybody got that? All right, so let's just add up our constraint equation here and see what it looks like. 240 equals. All right, it looks like we've got 20x plus 10x is 30x. So we've got 30x. And then it looks like we have a plus 20h. And then it looks like we have a plus 20xh. I just added it in one row going down. Alrighty, let's try and reduce this thing a little bit. First of all, dividing by 10 would be easy. So we got 24 equals 3x plus 2h plus 2xh. Just divide through by 10 to make it look a little easier. All right, we're going to have to solve for either the x or h to get it all in terms of one variable, and they all look equally awful. So which one would you like to do? Just pick one. You want to solve for x? All right, remember, if you're solving for x, all terms with the same variable have to be on one side. So we have a 3x and a 2xh equals 24 minus 2h. And how do I get x by itself here? Factor. You got to factor out the x to separate it. 3 plus 2h. I call that the big F word, factor. 24 minus 2h. So x then is 24 minus 2h over 3 plus 2h. Okay? All right, we haven't done anything hard yet, right? That's all algebra right there. And the formula for volume of a box, we're still geometry kind of deal. All right, now we're going to replace x over here with 24 minus 2h over 3 plus 2h. All right. So volume is 24 minus 2h over 3 plus 2h times h. And personally, I think it would just be easier to distribute that h through before I take the derivative, because we got to maximize, we'll take a derivative. So volume then is 24h minus 2h squared over 3 plus 2h. H is the same thing as h over 1. I just distributed the h through the numerator. Everybody good? All right, so we want to maximize volume. So we're going to take the derivative, and we're taking it with respect to h. What rule are we using? Quotient rule. Go ahead of me so you can check my arithmetic. Are we good? Okay. Let's clean this up. Do you see any common factors? I don't see any common factors. So it looks like we need to distribute here. So 3 times 24, check my arithmetic, that's 72 minus 12h plus 48h minus 8h squared. And I'm going to distribute my negative with the 2 at the same time, so that's going to be minus 48h plus 4h squared. Please do not let me make a mistake. Is that good? Negative times a negative made that a positive. Thank you for checking. Am I good? The reason I'm having you check is because if I mess this problem up, it's your fault, not mine. All right, let's see if I can clean that up now. Negative 8h squared and a plus 4h squared would be a negative 4h squared. Okay, 48h minus 48h, that's great. They cancel each other out. And now I have a minus 12h plus 72 over 3 plus 2h quantity squared. All right, I believe I can factor a 4 out of that numerator, can I? Maybe a negative 4, and that would give me a h squared plus 3h, and 4 goes into 72. Please tell me 4 goes into 72. 8 times? 18? Yes, 18. I was trying to do that so I could factor. All right, so we've taken the derivative. And we know that a max or a min will occur where we set that first derivative equal to 0 or undefined. All right, well, if you were looking down in the denominator, what makes that denominator equal 0 is a minus 3/2. But h is the height of my box. So we know we don't even have to worry about that, what makes it undefined, right? Okay, so let's just go to the numerator. We're going to set it equal to 0. So we have negative 4, and I'm going to factor the h squared plus 3h minus 18, and it factors to h plus 6, h minus 3. Correct? Again, I'm not worried about the denominator because that's a h value negative, and it's a box. That's called a extraneous solution when it wouldn't work. All right, so when we set this equal to 0, h is either going to be 6 or h is going to, h is negative 6 or h is 3. I only got one possibility that can work here. What is it? H is 3 because h represents the height of my box. You could go back and put in your derivative to show that that gives you a max. But usually with these word problems, and definitely all the ones you get, the answers are going to be so ridiculous, like negative heights or something, that the only one answer that comes out is going to be the one that works. Okay, but they can be verified. So that's not too bad. You just got to be careful working through. All right, everybody good? You don't like algebra? I take that you love calculus, though. It's great to apply that. All right, let's keep backing up in our book. So 3.1 was product and quotient rule, and we just applied it. All right. Okay, when I'm in 2.7, what I want to remind you of, like in number 8, which was a problem we did in class, demand equation. Demand is the price for the item. So how does that relate to revenue? Revenue is price times X. Yes, the quantity that you sell. So the revenue function here would be P times X, demand equation. In terms of cost and revenue and profit, this one is going to be maximizing profit. So you know profit is revenue minus cost. These are problems we've already done in class. Okay? On page 207, number 14, you had some web-assigned questions like this with the trees, and that supplementary sheet I gave you had trees and tickets. It's on the website, Vista. This was where you knew if you didn't make any changes what your revenue would be coming in, but they found out that every time they went up on the members, they could reduce the membership fee. Remember, we went through a few so you could set up your formula. And then once you got your general formula, we usually let X be the unit of increase, decrease. Remember that? Then be sure you answer the question, how many memberships? So you had to go back to the part of the equation that was memberships, which was probably something like 100 plus X every time you went up a member. All right, so you're going to expect a demand equation on your test. Cost, profit, revenue deal. You're going to expect a problem similar to number 14, which is trees or membership or sidewalks. Number 15 was a problem we did that involved sidewalks, okay? And those are on the sheet, okay? The supplementary sheet that's on Vista. Okay, 2.6, section 2.6. When I'm looking at 2.6 on page 197, I had highlighted here problem number 13. I don't know if we ever did that one or not. Let's just look at it and see. It is, do you remember if we did 13? I can't remember if we did, but I see a highlight here. This is referring to the figure B. It says that this rectangular corral of 54 square meters is to be fenced off and divided with fences all over the place. All right, so the corral here is to have 54 square meters. Somebody translate what that means. The area is 54 square meters. So what is the formula for the area of this thing? X times W. That's going to be your little constraint equation. X times W is 54. All right, find the dimensions of the corral so that the amount of fencing required is what? Minimized. So the amount of fencing is minimized. Where's the fencing going? All around these places. All right, so give me the formula for the amount of fencing based on this figure here. It would be 3W plus 2X. That is the formula you're going to, 3W, because that's where fencing's going, 2X's. That is what you've got to minimize. All right, but you got to get your area in there because there's too many variables. That's pretty straightforward, isn't it? What's your constraint equation again, everybody? XW equals 54. So use that to get the 3W plus 2X in terms of the same variable. All right. The other thing, though, from 2.6 that you wanted to be really good at were your inventory problems. Inventory. Be sure you define your variables. You're expecting an inventory problem. X is the number of units produced or sold. X is the number of units that you purchased at one time, called the lot, L-O-T size. R is the number of orders per year. So you look at what they're charging you. Sometimes you got to remember to look, are they basing it on the maximum inventory, the insurance, as in problem number 8, whereas in problem number 4, when you go back and look in your notes, this was based on the average number in inventory. So when you get ready to place your order or buy your insurance, is it times X over 2 or is it over X? So the questions will tell you on the test. All right, inventory. All right, and then 2.5 was just a lot of geometry type problems. Number 16 we did in class, your closed rectangular box with square base. All right, let's look at that square base because you had a question about that. Okay, look back in your notes on page 187 at problem number 16 because I know we did that one in class. When you draw a rectangular box, if I can draw it so you can see it. Okay, and here's my bottom of my box if you can see it. All right, when the problem says a rectangular box with a square base, here's your base, so its units have to be, say, a X by X, where the problem we just did, it was not a square base box. And then you got some height, H. This particular problem is a closed rectangular box, so it has a bottom and a top. But if it says open, then you would just be worried about a bottom and no top. Okay? Everybody good on that? All right, so if you were doing the volume of this box, it would be X square H, correct? Area of the bottom times the height. All right, and here in this particular problem, you were minimizing cost of materials. So you know you're going to the surface area to minimize. It told you what the volume was, 12. All right, we did that one in class, so I'm not going to go any further. You can go back and look in notes for that. Okay? All right, so be careful when you're reading your questions on the test. Focus in on what you're maximizing or minimizing. Get that formula. That's what you're going to take the derivative of. There will be some other material, some other information in there that helps you get it in terms of one variable. All right? Okay. 2.4, etc. was curve sketching. I feel like we've done pretty good on that. Let's just say it again. When you start to graph a problem, you always check out your domain, any y-intercept that you have. If the x-intercepts are easy, get them. If they're not, leave them alone. Are there any asymptotes? When you take your first derivative, you're only going to know if the curve goes straight up, down, or straight across. Straight across is where you have that horizontal tangent line at a point. All right? Your first derivative equal to 0 or undefined are possible what? Extreme points. You don't know if they're an extreme until you check around it. All right, so once you know if it's increasing, decreasing, or horizontal, you go to your second derivative for shape. So when your second derivative is greater than 0, that tells you concave up. So go over your line going up or down and give it a concave up look. And if your second derivative is less than 0, so concave down. And if the concavity changes around a point, that point's called a inflection point. Okay? All right. I think we're okay with that. We worked real hard on that already. When I flip back to 2.1, they were trying to introduce you to the terms 2.1 and 2.2. 2.1 and 2.2. I'm on page 159. These were asking you information at a particular point instead of sketching the whole graph. When you're very near exit 3, they tell you a point. They tell you the slope at that point. They tell you the second derivative at that point. And based on that information, you could tell us a little bit about the graph and make a good sketch. For example, in number 14, you had the point, 3, -2. The first derivative at 3 being 0, that told you to do what? Horizontal tangent line there, possible extreme point. Second derivative positive told you to concave up. So that ended up being a minimum point. Okay, let's look at number 17 and let's just do it. F at 3 equals -2. What does that give you? The point 3, -2. The first derivative at 3 is a +2, so what does it tell you? Increasing. So you take that point 3, -2 and just put a little line that's going up through it. Okay, the second derivative of 3 is positive, so that tells you concave up. So when you plotted your point, let's see if I can find a little piece of paper here. So when you plot your point 3, -2, which is somewhere right here, 3, -2, that first derivative positive, you did a little line going straight up, correct? And then with the second derivative positive, you came back and made that a, oops, you can't do it like that. It's got to be like this. Because it's always got to be increasing. Increasing concave up. If I did like that, that part's decreasing. So always make it increasing like this, and then kind of concave it up like this. Okay, so concave up. There's your point 3, -2. Everybody got it? Okay. And then that take pretty, oh, what does it mean? What's the difference between the words function increases and slope increases?
The first derivative.
Okay, good. Function increasing just means your curve goes up. Slope increasing means concave up. How's the slope increasing? I think you guys are good at that. You got it. Okay, and then 1.8. This was using your derivative as a rate of change and the interpretation. If you have cost, the first derivative at a value gives you, if you got a cost function, the derivative cost function is marginal cost, and marginal cost tells you the extra cost for producing the next item wherever you happen to be. So at 2,000 here, when you're already at 2,000 units, the cost to produce one more radio, it looks like, would be $10. Okay? I think we did a pretty good job on that. All right, a couple questions from Webathon that were handed to me. Let's see if we can find the mistakes. All right, and this, I meant to do these in order, but now we're jumping around because I forgot to go back over them. This is homework on homework 9. And don't forget, after the answers pop up, there should be some video links to some of the problems, so you can go back and look at them. All right, here's the function e to the 5x squared, and here's the work for the problem. 2 e to the 5x to the first, e to the 5x times 5. Somebody help me out here. What's the problem? What's the concern? Tried using the general power rule. It is not a function raised to a constant, but a constant raised to a function. So we got to do e to the u. All right, so let's do this one together. Where am I going to write? Anywhere? Y equals e to the 5x squared. So the derivative is e to the u, e to the 5x squared, times the derivative of the u, which is 10x. Okay? All right. What you started out doing, and I see where you were coming from, this is not equal to, this thing is not equal to e to the 5x quantity squared. And that would be bring your 2 down, rewrite, decrease by 1. If you use your properties of exponents here, power of a power, that would be e to the 10x. Okay? I finally figured out where your thoughts were going wrong. The whole function is 5x squared. It's not the whole thing squared. Okay. Everybody see that? Because this is actually equal to e to the 10x, which is not the same thing as this. Okay? All right, the next question somebody had was more rules for derivatives. More rules for derivatives. And let's see if we can all find the mistake here. And the question was from F. Let's see if I can put it beside it. Oops. There we go. Right there is perfect. All right. There was a question about F. It says, find the derivative of, read that to me, everybody, x times f of x. All right, so when you hear x times f of x and you're going to be doing a derivative, what rule are you going to? Product rule. All right, so let's see if we can work out the words for the product rule. I was given the numbers here, but I need to know. Product rule is first times the derivative of the second plus the second function times the derivative of the first. Oops, which is 1. Right? Times 1. Everybody right? Okay, now let's see what the answer is supposed to be. The information we were given is that alpha 5 is 3. So all of these are being evaluated when x is exactly equal to 5. So there's 5, check. The derivative at 5, is negative 3, that's a check. The function at 5 is 3. Oh, the derivative of x here is?
I thought x was 5, so the derivative of 5 is 0.
Okay.
Which is where I got
The derivative of 5 is 0, but the derivative of the function at 5 is negative 3. Remember, when you're going to take a derivative, you're finding a formula first, and then you go back and substitute in. So when you took the derivative, it was the second function times the derivative of the variable x. The derivative of the variable x is 1. Then you go substitute your 5's in. Does that help? Thank you. I can see how that mistake happened. All right, yeah. Don't ever plug in anything and any numbers into your derivative until you've got your derivative done. That gives you a general formula for the derivative, and then plug numbers in. Oh yeah, same thing here. There's where your mistake is in the last one. The bottom, which was x, is 5 times the derivative of the top minus the top times the derivative of the bottom, which is a 1. Okay? Good, thanks. All right, send those back. Glad we got those straight. Okay, and then the next question was off the homework 7, had the little peach orchard. When 40 trees are planted, you get 500 peaches per tree, so the yield would be number of peaches. Every time a tree is added beyond 40, the yield is reduced by 10 peaches. All right, so the problem is, where's your number 2? Okay, so let's see if we can find the mistake here. All right, so just like I always like doing things, 40 trees, you get 500 peaches per tree. It gives you a yield of 20,000 peaches. See, this unit is peaches per tree. So your trees divide out in your units, and that's how you get your 20,000 peaches. 1, 2, 3. Oops, I think you got an extra 0 in there, don't you? 1, 2, 3, 1, 2, 3. Oh, 20. Okay, no, we're good. All right. So x was your unit of increase decreases. So you started playing with it. Every time you add a tree beyond 40, so 40 plus x is your number of trees. Does everybody agree with that? The yield is reduced by 10 peaches per tree. Okay, what happened right here? You said it's reduced by 1 unit. It should be 500 minus 10x. See, if x happens to be 1, you went up on 1 tree, you got 41 trees. But it meant that you had 500 minus 10 or 490 peaches. Does that make sense? Are you good? Who gave it to me? I already forgot. You did. Are you okay? Okay, so here's your little mistake. All right, so you did everything so good until that one little place that caused major problems. When you write out your formula, go back and practice when x is 1, when x is 2, does this equation make sense? And if you know it does, then you're ready to take the derivative. All right, good? Everybody good? All righty, that's it. Yes?
After you find the derivative, that it equal to 0?
Right.
And that's the answer?
No. His question was, after you find your function and you take your derivative and you set it equal to 0, is that your answer? Well, that's going to give you your value for x, and what did x represent? Unit of increase, decrease. The question is number of trees to maximize crop. So which one of these was trees? 40 plus x. So you got to go, that's why it's so important you label your variables. X is unit of increase, decrease. 40 plus x is trees. 500 minus 10x is number of peaches. Because the question could say, how many peaches per tree should you be getting to maximize your yield? So whatever you got your x, go put it back in so that you know it. Thank you so much for asking that, because I can't tell you, people on the test are so excited to get done. You get your x and you forget what the question was. So I would just encourage you too, when you're reading problems on a test, I always encourage students, highlight, number of trees, maximize, so that you know, keep reminding yourself what it is that you're trying to get to. Okay? All right, I think that takes care of it, and I believe you can do well on your test, and I can start us on logarithms, which I need to really bad. Are we okay? We'll do good on the test. All right. So this is beginning of test 3 material. Do you need to stand up and stretch a second? Do. Stand up and jump around. Lead the exercises. Quickly while I write this down. You don't want to lead exercises? Not certified. Oh, you're afraid if you injure somebody here, we're going to be suing you. Okay, beginning of test 3, we are now in chapter 4, and we're just going to do a little algebra review real fast from logarithms. 4.4, and we want to talk about the natural logarithmic function. And just in case you don't realize this, this is called review. You may need to look back in your pre-calculus book for some help here. Alrighty, I like to begin where you've been so far. So far, you know all about y equals e to the x. Y equals e to the x, the natural exponential function. And everybody knows it looks like this. You have the point 0, 1. You have when x is equal to 1, you have y value is e. The natural exponential function, you remember the domain is x is all reals. The range is y is greater than 0. And you'll remember your asymptote is the line y equal to 0. You had your asymptote right here. Okay? Then you remembered one of the fun things math people like to do is talk about inverse functions and look at all of its properties. And you know that this function has an inverse because it is 1 to 1. 1 to 1. All right, what do you remember about inverse functions? Inverse functions. How do you find an inverse function of an algebraic?
Change the X and Y.
You change the x's and y's, and you're also interchanging domains and ranges, right? That's what interchange x and y is. So for our problem, the inverse function, now the domain becomes the range. The range is that y will be all real numbers. The range of y equals e to the x becomes the domain, so x is greater than 0. The asymptote now will be x equal to 0, just interchanging those. Interchanging x and y, instead of the point 0, 1, we have the point 1, 0. Instead of the point 1e, we'll have the point e1. And our asymptote, of course, is the y-axis, and it looks like this. That's our inverse. It's a reflection across the line y equals x. And the name given to that is y equals natural log of x. Okay, and that's our natural log function. Y equals natural log of x. From this, just interchanging x and y, you see that the natural log of 1 is equal to 0. That's one of those little things you memorize. Natural log of e is equal to 1. Those are some basics that everybody memorizes. Okay? And natural log is really, if you have y equals natural log of x, that is really log to what base? No, e. Log to the base 10 of x is called common log, and you see log. And if you're on your calculator, where you see your natural log button, ln, you'll notice that the second function right above it is e to the x. That's because they're inverse functions of each other. Log, common log, and right above it is 10 to the x. So common log is base 10. Common log and 10 to the x, they're inverse functions of each other. Okay, so most physical problems are with natural exponentials and natural logs because they're the easiest to work with. Okay, and we're concentrating on natural exponentials and not natural logs for our class. Okay, there's a couple other little identities that you memorized, should have in pre-calculus. Okay, they were called identities. And these come into play and are actually kind of important at times. And this really just came from, hopefully your instructor showed you the composition of functions to get it. One property is e raised to the natural log of x. E raised to the natural log of x. Who remembers what that's equal to? X. And that comes from, again, a composition of functions. And then you have natural log of e raised to the x. You may remember what that is equal to? X. And these were two important identities. And you're just, it's just a composition of those two functions. Since they're inverses of each other, they cancel each other out. Either natural log of x is x, natural log of e to the x is x. And one reason you do something like that is, back in the pre-calculus days, if you had e raised to the x equals 7, and you needed to solve for x, if you were to solve for x, then what you do is apply this identity by taking the natural log of both sides of your equation. Take the natural log of both sides of the equation. Just like you can add something to both sides, you can also take the natural log of both sides. And the natural log of e raised to the x is x, so x is natural log of 7 is your answer. Or you had a problem that looked like this. The natural log of x equals 12. and when the x was part of the argument of the log, to get rid of the log, we call it exponentiate both sides, but I haven't seen that in any precise encyclopedia of mathematical vocabulary. All right, I have seen it in a couple papers that were published, but I really haven't seen it in this big, thick volume of encyclopedia of precise mathematical vocabulary or definitions or words or something like that. Exponentiate was not a word, but I've seen it in other places, so I'm just going to use it. So what you do is, like here you took the natural log of both sides. Here you, what some people call exponentiate both sides, which just means you're going to let both sides of the equation be the exponent for the e. And now you have e to the natural log of x is x. And so you get e to the 12. So when I was teaching pre-calculus, I used to tell my students when you have an exponential equation and the variable is in the exponent, exponential, take the log of both sides. If you had a log equation with the variables with the log, then exponentiate both sides because they work in inverses of each other. All right, so that is basically what 4.1 is all about. 4.4, I'm sorry, 4.4. 4.4. On page 264. And really all they're wanting you to do here is apply some properties, identities. If you look at number 7, the natural log of e raised to the negative 3, the natural log of e to the, instead of saying x, just go natural log of e raised to the m is m. It doesn't have to be an x there. You can let that unknown be a m or whatever. So the natural log of e to the negative 3 is what, everybody? Negative 3. Okay, let's look at number 11. What is the natural log of e equal to? 1, and then the natural log of 1 is 0. So they're just wanting you to apply these things. Okay, in number 13, I'm going to have to use one of my little properties of logarithms before I simplify that. That 2 in front of the natural log of x, using a property of logarithms, where else can I put that little 2? Okay, that would be the log of, let me write that down because it might be hard to see what I'm talking about. Remember we had some properties of logarithms from pre-calculus that if you had log, I'll just do natural log. Natural log of m plus natural log of n is equal to natural log of what? M times n. Natural log of m minus natural log of n is equal to natural log of m divided by n. And then the one that I'm trying to get to was a third property, which is natural log of m raised to the p. What is that? P natural log m. So when we're looking at the problem number 13, which is e raised to the 2 natural log of x, this is number 13, we want to apply this property in reverse. So you get e to the natural log of x squared, just using that property in reverse. So now our property says e to the log m is m. So e to the log x squared is, it's not a trick question, tell me. Whoa, y'all are tired. E to the log, let's make these m's instead of x's here. Natural log of e raised to the anything is the anything. Natural log of e raised to the m is m. So e raised to the natural log of x squared is x squared. Okay, so it was requiring you to recall one of your properties of logarithms that you learned in pre-calculus. All right. You might want to, okay, test is tomorrow. Next lecture, before you come back, be sure you go through the section on natural logarithms, and you may need to pull out your pre-calculus book to review a little bit because we're going to get into the derivatives. Have a great day, everybody. I'd like lots of hundreds on the test.